Hello everyone, welcome back, and in today's video you're going to be solving some AITS problems from mechanics and electrodynamics. So the first question is going to be based on the ideas of center of mass. So two blocks B and C are connected by a light spring whose force constant is K. Then we have a third block whose mass is exactly the same and it is placed at a distance of L from the block C. So now the block A is moving at the velocity of V naught. It collides with the block B and it's given that all the collisions are going to be elastic. So we need to find the minimum value of L for which the block D, which is this block, also moves with the velocity of V naught after all the collisions. So this problem is kind of taken out from Pathfinder. It's in the chapter of oscillations. So now let's try to solve this. So okay guys, so firstly, if we have two blocks whose masses are equal and one block is moving with a velocity of V and the other is at rest, and if I give that the collision is elastic, then after collision, the first block will come to rest and the second block will gain the same velocity v with which the first block was coming. This is a very easy concept, so we are going to be using this here. So keeping in mind that, so after A collides with B, A's velocity would become 0, so it's pretty much useless afterwards. A's velocity will become 0 and B will gain a velocity of V naught. So we can just analyze this system over here and forget about A. So this is our starting situation. So what's going to happen after this point is that as the mass M moves towards the right, it is going to compress the spring, and because of the spring forces, this M is going to speed up, this is going to decelerate. And the best way to analyze the motion of this combined system is to view it through the lens of the center of mass frame. So let's first figure out the velocity of the center of mass. So that is pretty easy to figure out. It is m1 v1 plus m2 v2 divided by m1 plus m2, which is simply v by 2. So relative to the center of mass, this block will initially have a velocity of v by 2 towards the right, and this block will have a velocity of v by 2 towards the left. So now in the CM frame, they're going to be performing SHM. So you can kind of treat this CM line as a wall and this as a spring mass system, but you have to keep in mind that the spring constant you have to take in this case is going to be 2k, right? Because the spring length is now halved. So now the time period of oscillation for this spring mass system on the right is going to be 2 pi square root of m divided by 2k, and this is the same result you obtain with the reduced mass. What this essentially means is, so in a time t, the block will complete one oscillation. Okay, so now the question is, guys, we want the velocity of this mass to be v as well after collision, and so in order for this mass to gain a velocity of v, when this mass is about to collide with mass m, it has to have a velocity of v, right? Because only then will this mass m gain the same velocity v after colliding. Okay, so all we have to do is ensure that this block over here has a ground frame velocity of v when it is about to collide with this mass over here. Okay, so when will this mass m have a ground frame velocity of v? And the answer is pretty simple. So initially it has a velocity of v by 2 to the left, right? So after it reaches the extreme position, comes back to the mean position, now it will have a velocity of v by 2 relative to the center of mass frame. So now if you superimpose the center of mass velocity to this, you can see that the ground frame velocity of the block is now v. And this happens after a time of t by 2, right? Because to go from mean to extreme, it takes time of t by 4, and to come back from the extreme to the mean position, it takes another t by 4. So after t equals t by 2, the ground frame velocity of this mass is going to be v. So now we have to ensure that in a time of t by 2, this mass m should be over here. So now we have to analyze the displacements. With respect to the CM frame, guys, this particle will go to the extreme and come back to mean. So relative to the CM frame, the displacement of the particle in a time period of t by 2 is 0, right? Because it goes to the extreme and comes back to the same position. So it didn't displace at all. So if you want to make sure that relative to ground frame, this mass covers a distance of L, then we have to make sure that CM covers a distance of L, right? The center of mass, the distance covered should be L, and we know the velocity of the center of mass is v by 2. This multiplied by the total time period of t by 2. So basically, in a time period of t by 2, the Cm should cover a distance of L. So if this equation is satisfied, then this mass will have a velocity of v. Okay, so now all you have to do is compare this with this thing and you obtain n equals 0.25. So now let's move on to the next question. So in this question, we have two rods of the same mass and length, and they are rigidly hinged together at this point B. Now the point B is not hinged, guys. So these two rods are hinged at the point B. And then we have a particle A that is coming with a velocity of u perpendicular to AB, and it collides with the point A. And it's given that the particle stops after collision. So in that case, we have to find the angular speed of the connected rod after collision. So now let's get into the solution. So the only thing you have to keep in mind in this question is that you choose the right point to conserve angular momentum. You cannot choose a physical point on the rigid rod to conserve angular momentum and say that the angular momentum is conserved. Okay guys, so the reason for that is you can only apply this equation tau equals dl by dt provided one, if the point is non-accelerated, or if it's the center of mass. So tau equal to dl by dt is only applicable under these two conditions. Okay, now let's say if you take a point on the rod's frame that is literally on the material of the rod, then during collision there is clearly going to be some force that the mass applies on the rod, right? And because of this force, this point is going to accelerate. So all the points on the material of the rod are accelerated. So like for example, you cannot pick the material point B over here and apply angular momentum conservation, because B is an accelerated point and accelerated points do not satisfy tau equal to dl by dt. So you cannot say that angular momentum is conserved. So if you say, let's say you took the point B that is attached to the rod, then, and if you say MUL is equal to I about B times omega, this would be wrong. But the thing is, you can choose any point as long as it is non-accelerated, right? Or you can even pick the center of mass, it's up to you. So if you like, let's say if you want to do it about the point B, okay, so you can choose the point B, but you cannot choose the point B on the rod. So the thing is, I'm choosing this point B that is outside of the rod on the ground, that is going to be a fixed point. So the B I am choosing is not attached to the rod. And the reason for choosing that is now it's a fixed point, so it's non-accelerated, right? So now you can conserve angular momentum about the point B. So the initial angular momentum is only due to the mass, which is going to be MUL. Now guys, the angular momentum of a rigid body about a point is nothing but the angular momentum of the center of mass plus the angular momentum of the rod relative to the center of mass, right? So I'm just going to be choosing the center of mass here. You guys can take the fixed point B and do angular momentum conservation. If I choose the point B, then I have to calculate the angular momentum of the center of mass about the point B. So instead of that, I'll just choose the center of mass. So that will make the calculations easier. So CM of this rod is over here. The CM of this rod is over here. So the combined CM will be at the midpoint of this line segment, which is over here. So by symmetry, we can see that this length is L by 4. Mass M is at a perpendicular distance of 3L by 4, right? So the initial angular momentum is going to be MU times 3L by 4. And finally, it is just going to be I above, and for final angular momentum, we need the I about the center of mass. Now, so the I about the axis passing through this point is ML square by 12. So all I have to do is add another MD square to it. This is L by 2. So this is going to be root 2 times L by 2. This distance is going to be L by root 2. So this distance is half of L by root 2, which is L by 2 root 2. Okay, so I about the CM is nothing but ML square by 12, which is the ICM of the rod, plus M times L by 2 root 2 squared, which is L squared by 8. So this comes out to be 5 by 12 ML squared. So just after collision, the angular momentum is going to be 5 by 12 ML squared times the omega, which is the angular velocity of the rigid rod. So after solving, we get omega as 9u divided by 5L, which corresponds to option A. Okay guys, so this is the third problem. So we have a uniform rod with mass M and length L that rotates with a constant angular velocity omega about the vertical axis passing through the rod suspension point O. So basically it is rotating like this, okay? So it is rotating around this axis. So in doing so, the rod describes a conical surface with a half aperture angle of theta as shown in the figure. Then choose the correct options, okay? So we have to figure out the omega, the reaction force at the point O, the torque due to centrifugal force, and we also have to figure out the magnitude of the angular momentum. Okay, so let's deal with them one by one. Each point on this rod is going to be moving in a circle about this vertical axis over here. So if you want to figure out the omega of the rod, all you have to do is pick up any particular point on the rod, observe its motion, and as you can see, it's a circular motion, right? And if you curl your fingers in the direction of the circular motion, you'll get the direction of the omega vector. So the omega vector in this particular case is going to be in the z cap direction. Okay guys, so now this is one of those problems where you could not write L vector as I multiplied by omega vector unless you write down the tensor definition of I, which is not in your syllabus, which I have made a brief video about, which I'll link it in the description below. So I also discussed a problem similar to the 2016 rotation problem in that, so you can check it out. So basically L vector does not coincide with the omega vector in terms of direction. Then what is the direction of L vector? So let's figure that out. So if I want to find out the angular momentum vector about the point O, so then I'll just simply use the basic definition of angular momentum, and that is sigma of mi ri vector cross vi vector, right? Where ri is measured from the point O. So let's say I take some dm mass over here, which is at a distance of r. So from the diagram, I can easily see that the velocity vector of this dm mass is going to be into the plane, right? So this is r vector, v vector is into the plane. If you do r cross v, you get the direction perpendicular to the rod. So if you similarly do sigma mi ri cross vi for each of these elements, you will figure out that due to each of these elements, the direction is just coming out to be perpendicular to the rod. So the angular momentum vector is going to be perpendicular to the rod. Let's call it LO vector. So let's say after rotating by an angle of 180 degree, so the rod will reach this state. And in this situation, the angular momentum vector will be in this direction, right? If you similarly do mi ri cross vi for each of these elements, you'll figure out the L vector is now in this direction. So as you can see, the L vector itself is rotating with the same omega that our rod is rotating with. Okay, so now, we have kind of gotten a feel for the direction of the angular momentum. So now let's talk about its magnitude. Now guys, in order to change the angular momentum vector, you need a torque, right? You need a torque. If there is no torque, angular momentum vector does not change. But we clearly saw that the angular momentum vector was changing in direction. Now, in order to change the magnitude of L vector, we need a component of dl or tau. Tau is basically dl by dt. So I need a torque or dl in the direction of L vector in order to change its magnitude, right? But if you observe the point O and if you try to figure out the torque about the point O, there is only one force that has a torque about the point O. And if you do R cross F for mg, then what you obtain is the direction comes into the plane, which as you can see is perpendicular to L vector. So the net torque is coming out to be perpendicular to the angular momentum vector, which means it can only change the direction of the L vector and not its magnitude. Therefore, the magnitude of the angular momentum vector remains constant. So in option D, what they're asking is the magnitude of the angular momentum. So let's just try to figure that out. Again, we'll use this simple definition. Now, as this is a continuous rod, guys, we instead of using the sigma notation, we'll just use integration. So this will be integral of dm r cross v. Now, as we discussed, r vector and v vector are perpendicular to each other. So we can drop the cross product and write it as r into v. So this would be integral of dm. And by the way, this is r vector. So dm multiplied by r. Now v we can determine using omega, right? So this is the axis of rotation, and the distance of the point from the axis of rotation is going to be r sine theta. So the velocity of this point is going to be omega r sine theta into the plane, but omega r sine theta. So I can take out the omega sine theta outside. This will simply be integral of dm r squared, and integral of dm r squared is the moment of inertia of this rod about this axis, okay, and which we know it is simply ml square by 3. So this comes out to be m omega l square sine theta divided by 3, and which does not match with this option, so option D is wrong. Okay, so now we are going to find omega vector, and for this we'll use the fact that tau about O is equal to dl by dt about the point O. So first let's figure out the most easiest thing, that is the torque of mg. So mg acts at the center of mass of this rod, right, and it acts vertically downwards. So this distance is going to be L by 2 sine theta. So tau of mg is going to be, in terms of magnitude, it is mg L by 2 sine theta. Okay, so now this angle is given to be theta. I can figure out even this angle is theta. Okay, so now as I discussed that L vector's magnitude is constant. So if I split it into two components, guys, I can say that there is an L cos theta component and an L sin theta component. So this L sin theta component, as you guys can see, it will always be in this vertical direction along the omega vector, and its magnitude is also not changing. So this L sin theta vector is not changing. But if you observe this L cos theta, it is going to rotate in a circle similar to how this rod is rotating. So what I'm going to do is I'm going to observe this L cos theta from top and draw a top view of that in the next page. Okay, so let's say this was the initial state of the L naught cos theta vector. Now let's say it rotated by a small angle of d theta. So what is the change vector? So the change vector is going to be this vector over here, and we can easily name it as dl because this is the only change in the angular momentum vector. So now we can use the arc length formula and write dl as L naught cos theta, which is the radius, times the angle, which is d theta. So now what I'm going to do is divide both sides by dt, And dl by dt, I can say that it is a net torque about the point O, and this would be equal to, which is also the net torque due to mg, and this would be equal to L naught cos theta multiplied by d theta by dt. Now, as I said earlier, this L vector rotates at the same angular rotation rate as this rod over here in order to maintain the fact that L has to always be perpendicular to the rod. You can imagine this like another rod that is rigidly attached to, and they both rotate with the same omega. So basically we can say that d theta by dt is the same as omega. So this will be L naught cos theta multiplied by omega. Now the torque of mg we determined in the last page. It was mgl sine theta divided by 2, and this would be equal to L naught. And after substituting the values, you obtain the value of omega as this particular value and matches with the option. So option B is actually correct. So now in the third question, they're asking us about the component of reaction force, which means a hinge reaction at O in the horizontal direction. So for that, we have to write F equals ma, right? And for writing F equals ma, we need the acceleration of the center. So if you observe something, the center of mass is actually moving in a circle of a radius of L by 2 sine theta. So its acceleration is towards the center, and its magnitude is omega square times the radial distance, which is L by 2 sine theta. So now we can simply write F net equals ma. So now the only real force that is providing this acceleration is the hinge force, right? Which will be in this direction. Let's call it Fh, because there is no other horizontal force acting in the system. So I can in one step write Fh as m times the acceleration, which is omega square L by 2 sine theta, which means option C also matches. Okay, now in option A, they're talking about the torque due to centrifugal force. Okay, so this problem, there is a shortcut to doing this. Like, we don't have to do anything in order to solve this. So in the rotating frame, obviously there'll only be one more force, that is the centrifugal force, right? So in the rotating frame, we have two torques, torque due to mg and the torque due to centrifugal force. So basically the net torque in the rotating frame has to be 0, because in the rotating frame of reference, this rod will be at rest, right? So which means the torque due to gravity and the torque due to centrifugal force, they both have to add up to 0. Which means in terms of magnitude, these two have to be the same. Now the torque due to gravity, we actually figured it out, right? It is mgl by 2 sine theta. But the options kind of match with this side over here. And if you observe the option in here, they are saying sine 2 theta, but here there is a 2 missing, right? So hence option A is wrong. So the answer to this question is B and C. We have a spherical charge distribution of radius capital R. So it's uniformly distributed throughout its volume. And then we have a spherical cavity of radius R by 3, whose center is at C. And 2 points A and B are on the surface of the cavity, lying on this straight line over here. So VA, VB and VC are the potentials electric potentials at point A, B and C. E0 and EC are the magnitude of electric field at the point O and C respectively. Then choose the correct options. Okay guys, so if we have if we have a sphere in which charge is distributed uniformly, so let's say its uniform charge distribution is plus rho and its center is at a point over here. So it has a spherical cavity whose position vector of the center, let's say it is O dash, and we want to figure out the electric field at some point P inside the cavity. So we're going to be using the principle of superposition of vectors. So if I assume a full sphere of charge distribution of plus rho, then I can say the electric field is going to be in this direction, is going to be along the PO vector direction, and its magnitude, I can write it as P times OP vector, which means vector from O to P, 3 epsilon naught. Okay, and similarly, and with this, I'm going to consider the contribution due to a minus rho charge distribution at this point P. And with that, we can get the net contribution. So if I consider the minus rho charge distribution, then in this case, the electric field will be in this direction towards the center O dash. So in this case, I can write the electric field as rho P O dash vector divided by 3 epsilon naught. So the net electric field is going to be the superposition of these two, which means this is rho by 3 epsilon naught times OP vector plus P O dash vector. Now OP vector plus P O dash vector is nothing but OO dash vector, and that is nothing but the vector joining the centers. Okay, so which basically means if I get rid of all these and call OO dash vector as some A vector, so everywhere inside the electric field is going to be of equal magnitude, and it will be in the same direction. So inside the cavity, the E field is going to be uniform and its direction is going to be parallel to OO dash vector, which means it will be in this direction. Okay, and the electric field is uniform because its magnitude is constant, as you guys can see from here. Okay, so in the first problem, they're asking what is the potential difference between VA and VC. So we just determined that inside this cavity, the electric field is going to be uniform and it is in the direction of OC vector, right? As I know the electric field inside, I can simply use the line integral method. So using the line integral method, I can say VC minus VA is nothing but minus integral of E dot dl from the point A to C. And we also know that in the direction of electric field, potential decreases. So now as the electric field inside will be in this direction, so with that we can say that the potential at A is greater than the potential at C and it is greater than the potential at B. Okay, so now let's figure out the electric field inside. Rho OC vector divided by 3 epsilon naught, and OC is nothing but 2r by 3 in magnitude. So this is going to be 2 by 9 rho r upon epsilon naught. So let's call it as some E naught. Okay, so I can say VC minus VA is equal to minus E naught times, so I can take E out of the integral because electric field is constant. Now integral dA from A to C is just the path length from A to C, which is going to be r by 3. Now similarly, even if you do VB minus VC, this will also come out to be the same E naught times r by 3. From here, what we observe is VA minus VC is the same as VC minus VB. So A option is actually correct. Okay. So now in the second option, they are saying VA minus VC is greater than VC minus VB. No, it's not true because they are equal, right? Now in the third option, they're asking the electric field at the point C. It is not rho r by 9 epsilon naught. It is 2 rho r by 9 epsilon naught. And in option D, they're asking the electric field at the point O. Okay, so electric field at point O also we can determine using superposition. So if I consider a complete sphere of plus rho, we know that the electric field at the point O is 0. And because of this minus rho sphere, now for this minus rho sphere, this is a point that lies outside the sphere. So I can use the formula of kq by r square. So I can treat this entire thing as a point charge placed at the center and write its electric field. So now the distance O dash, again it is 2r by 3. So the electric field actually comes out to be, again its direction is towards O dash, right? Because it's minus, because this is negative charge, and it comes out to be K, which is 1 by 4 pi epsilon naught Q, and the charge is rho times volume, and the radius of the sphere is r by 3. So this is going to be 4 by 3 pi r by 3 cubed. So KQ divided by the distance squared. So this is 2r by 3 squared. And this after calculation comes out to be rho r upon 36 epsilon naught. Okay, so this comes out to be rho r upon 36 epsilon naught, and its direction is in the O dash O vector direction. Okay, so option D is also correct. So this was the answer to this problem. So now let's move on to the next problem. Okay guys, so now moving on to the last problem of the day. So we have a ball whose radius is capital R, and it is uniformly charged with a uniform charge density of plus rho. And we need the electric flux across the ball's section formed by a plane located at a distance of A that is less than capital R. So they're talking about a plane, something like this, whose distance from the center is A. And we need the flux through this surface. So this is actually going to be a circular surface. So we have to figure out the flux through this surface over here. At a radial distance of r from the center, the electric field at this point is firstly radially outwards, and its magnitude is rho r by 3 epsilon naught. Okay, so the electric field itself is varying from point to point. Now let's say if I consider a patch of area on the surface, so I'll just draw the side view of the surface over here. Okay, so I am talking about a patch, something like this. Okay, and let's call the patch's area as dA. So we know the electric flux through this element. So if I write the electric flux through this element over here, it is going to be E dot dA, right? Which is nothing but rho r by 3 epsilon naught. Now dA vector, guys, it's going to be in this direction, normal to the surface, right? This is the direction of the dA vector. So let's say this angle over here is theta. E dot dA will be rho r upon 3 epsilon naught dA cos theta. And from here, we can see that there is a r cos theta term. And r cos theta is nothing but A, right, from this triangle over here. So this would be rho by 3 epsilon naught into A into dA. So now all I have to do is integrate this expression, and I'll get the net flux through rho A by 3 epsilon naught times the integral dA. Integral dA is nothing but the area of this circle, and the radius of the circle is square root of capital R square minus A squared, right? And you can see that from this right triangle over here. So this comes out to be pi times of capital R square minus A squared. So now we observe the options, it corresponds to option. So that was it for today's video, guys. If you enjoyed the video, do like, share and subscribe. And that's it. Thanks for watching.